Okay, so yesterday we have solved a word ladder problem and network delay time. So today we will solve this problem, reconstruct itinerary. So my last submission was in 23 for this particular problem. So let's read out this problem. So the problem says you are given a list of airline tickets where ticket I represents the departure and arrival airports of one flight. Reconstruct the itinerary in order to return it. Okay. Itinerary, a plan of a journey, including the route and places that you will visit. Okay. All the tickets belong to the man who departs from JFK. Okay. So we have tickets from this position to this position, and initially the man will depart from this particular position. Thus, the itinerary must begin from JFK. If there are multiple valid itineraries, you should return the itinerary that has the smallest lexicographical order when read as a single string. For example, itinerary JFK LGA is smaller lexicographical order than this particular. Okay, because here we have A and here we have B, so it is lexicographically, this path is lexicographically smaller than this particular path. So you may assume that all tickets from uh, all tickets form at least one valid itinerary. Okay, you must all the tickets once and only once. Let's read out the example. So we have this example, tickets, where we have tickets M MUC LHR JFK to MUC SFO to this to this. So initially we have these tickets, and we know we need to start from JFK because all the tickets to a man who departs from JFK. So basically these are the stations, means this is a code for a station. This station to this station we can assume these as the airports. I think from GFJ to MUC, then from MUC we can go to LHR, from LHR we can go to SFO, from SFO we can go to SJC. But I think we need to choose the path which is lexicography smaller if combined. For example, if we go from JFK to LGA, this is a mm, path in itinerary, but and also we can go from JFK to LGB. Then this particular path is smaller because uh, all the characters before A are equal, but A is smaller than B. So this particular string is lexicographically smaller. Okay, so you may assume that all the tickets form at least one valid itinerary. Okay, so we must have a valid path. So the question says, and we must use all the tickets once and only once. Okay, means we these are the tickets, so we need to use all these tickets. So in this particular example, what we are doing, we are going from JFK to MUC using this ticket. Okay, then MUC to LHR, MUC to MUC to LHR using this ticket, LHR to SFO using this ticket, and SJC to SFO to SJC. Okay, using this ticket. Okay. So conditions are need to use all tickets TS and need to one condition was also here and only once. Okay, and need a path which is lexiographically smaller. Okay, let's see the second example. So the second example says we have tickets on JFK, SFO. So we have these tickets. Okay, so from JFK here we can go to two positions. Okay, so we will go on this position and this position. Suppose we try to go to both the positions. So we can go from JFK to ALT, ALT to JFK, JFK to ALT, ALT to again JFK. Okay, because we have to use all the tickets. That's we are. That's why we are going again. Okay, so we need to keep track of tickets, the tickets we have used till now, and we need to keep track that we should not reuse a ticket. So we need to mark a ticket as visited. A particular ticket we will not reiterate again. If you first you check. Okay. So what we can do is first we can create a map, means from a particular node to nodes which we can go. For example, from GFK we can go to these nodes. So we need to create a map, something like a string and list of string. Okay, which will be our graph. Okay, so from current ticket, from tickets, what we need to do is we need to put it into our graph. So starting position for our graph will be tickets.get, ticket.get 0, and ending position will be v ticket.get 1. Okay, so we need to put it into our map at this position. If nothing is present, what we can do, we can put a new array list, and we can add v. So we have a edge from u to v. So we have created a map. can we print our map? No, we can't. We need to iterate the map to print it. Okay, so after creating map for this particular example, what we will get from JFK. So this will be our graph. Okay, so from JFK we can go to SFO and ALT. Okay, so we will have a SFO and ALT. And from then for SFO, we will have ALT. Okay, then for ALT we can go to JFK and SFO. So this will be our graph which we are creating. So suppose we call our DFS. So we need to start from the JFK graph. So JFK string initially. It is mentioned in the problem that man tickets belong to the man who departs from the JFK station. So this will be our source. JFK will be our source, and we will pass our graph. Okay. And we need to use all the tickets. Okay, let's call our DFS first. So this will be our source, and this will be our graph. So can we keep a track of visited? For example, for this particular pair, we can put a variable visited along with this SFO in our graph, like SFO, and suppose we put this pair SFO and false. This means SFO is not visited yet. We can also put ALT and false. Or we can put the index also here, like index of this particular ticket. If we put index, then we need to maintain a visited set, that particular ticket at the index is visited or not. Okay, so we need a itinerary which is like geographically smaller. So we will also maintain our current itinerary. So our current itinerary will be, let's use a string builder. String builder starting from JFK. So this will be our itinerary. So string builder itinerary. So if suppose we visited all tickets, if we visited all tickets, means we need a condition to verify that we have visited all tickets. Then in that case we will have something in our itinerary, that this is our current itinerary. So we will check if this itinerary is smaller than the itinerary we already have. Suppose we maintain a empty itinerary. Let's call this smallest itinerary. My old tickets used, and if my this itinerary is smaller than my global itinerary, so I have global itinerary here, then what we can do, we can okay, we need to have itinerary. So instead of this, what we can do, we can pass a we can pass this itinerary. And at the end we will return this smallest itinerary. Okay, we need to find out how we can track we if we have used all the tickets. Okay, so suppose we are at JFK. So from JFK we can move to SFO and ALT. So we will try to move into both directions. So what we can do, we can call the next stop. And how we can get the next stop, we can query our graph dot get source. So what this will do, this will iterate all the neighbors of let's remove this example and paste this example here. So what this will do, this will iterate to all the neighbors of our source, and try every itinerary. Like we will check see if this our current stop is not already visited, means if this current ticket is not already visited. So let's say if, so we are haven't defined these variables, we will figure out that how we will find this thing that all tickets are visited. And if next stop not visited, if our next stop is not visited, then only we will call our DFS, and we will mark our next stop as visited, means we have used our this ticket. And to our itinerary, what we will do, we will add this next stop. We have added to our itinerary the next stop, and we will call our DFS. So now our source will be next stop, and this will be our itinerary, and this will be our graph. So once we have visited path for this particular itinerary, suppose we have visited path for SFO, then we will visit path for ALT. So we need to remove SFO from our current itinerary. So how we can do this? We can itinerary dot remove itinerary dot size -1. So this will remove the next stop from our itinerary. Okay, this is for this, this is for this, this is for this, this is for this. Okay. Marking the next stop as the visited. Okay. Okay, so we need a visited array also. So in our graph, we will also need to store the index of the ticket. For example, JFK SFO, instead of false, we will store the index of this particular ticket. Then we can use, while iterating this graph, we can use that index to mark the ticket. We will add that to a set, visited set, and how we can check all the tickets are visited when its size set of the our visited size becomes equal to the size of the number of the tickets. Okay, so let's say we have a set which uses, which have integer visited, new hash set. We will pass this visited, and the number of tickets we have is the size of this array. So we will also pass the number of tickets. So it will be tickets dot size. So we will also use this n. And what? How can we decide that all tickets are used? We can check if visited dot size is equals to n. Then we can say that our all the tickets are visited. And we need to modify our graph also. With string we need to store the index, then we can only mark that particular ticket as the visited. So let's have a pair here. So we will define a pair like public class pair, which will include a string v and its index. String v dot, this dot v will be v, this dot, this will be idx. Okay, so next stop not visited. So now we will while adding, what we need to add, we need to add a pair. So what pair will include? Pair will include v and its index of that ticket. So what we need an index of this ticket. So what we can do, ticket get in. Okay, so this will be your index. So this is graph creation part. This is DFS part. So this will be our pair. So we can check if our set visited set doesn't contains this next stop dot index, then we can say this particular index is not visited, and we need to mark this index is visited. Now visited dot add next stop dot idx. Okay, after that we need to remove this index. So we can mark our smallest iteration. So now our smallest iteration will be uh, new array list, this particular iteration. So what this function will do, this will compare this current itinerary with the smallest itinerary. So it will return true if our current itinerary is lexicography smaller than smallest itinerary till now. Then we will update our smallest itinerary and we can return from here. So now we need to implement this function lexicographically smaller. Okay. Do our tickets have same size? Okay, so our tickets have same size, same length. So we can implement this function public boolean let geographically smaller. We will compare this itinerary with our smallest itinerary till now. So we can start from I equals to 0, I less than itinerary dot size, I plus plus. So its string, let's call current string as itinerary dot get ith string and string previous as the smallest itinerary till now we have and its current string. Okay, now we will compare, we will check if current is smaller than previous or not. If it's any point is greater, then we will say that we will not update. Otherwise, if it always smaller, at the end we can return true. So now we need to compare them. So as we know, our length can be ticket length is only 3. So as mentioned in the question, the tickets I dot length from dot length to dot. Okay, so from this station, so length is 3. So from j equals to 0, j smaller than 3, j plus plus. If current dot character at jth position is greater than previous dot character at ith position, jth position, then we will return false. That our current itinerary is like geographically greater than our already smallest itinerary, so we are returning false. In that case, we will not update our itinerary. So what we can do, we can cut this condition and will only update if our this itinerary is smaller. Okay. So let's once again read out the solution. So we have tickets, find itinerary. First we are creating graph. We are iterating our tickets. Let's say this in this example. We are iterating over our tickets. This is our current ticket, IA ticket, and we need to go from 0th U to V, 0th position to 1th position. Okay, then we are adding it to our graph, this edge with its index, the index of the ticket. Okay, now we are creating a list which contain the correct current path or itinerary. So we need to start from JFK. So we are adding JFK to our list. The question says all the tickets belong to the man who departs from the JFK. That the itinerary must begin with JFK. So we are adding JFK at first. Then we are creating a visited uh, set. Then what we are passing source will be JFK because we are initially starting from JFK. This itinerary graph and this visited and the size of the tickets, the total number of the tickets. Okay, so we have this source, this itinerary, this map, and visited set. We will see if our visited set size becomes n, means we have visited all the tickets. TSEK, then we will check if current itinerary we will have this will check if current itinerary is smaller than the itinerary we already have. So initially we have nothing in our itinerary. So one thing what we can do is we can need to also add a check that if our smallest itinerary dot size is 0, then we need to return true, because initially we don't have any itinerary, so we can't compare it with the previous itinerary, so we will return true. Return true, and we will update our smallest itinerary with this itinerary. Then from source what we can do, we can, so do we have pair here? Okay, we have pair will contain the position to which we are going and the index of the ticket. So this will be our next stop. Basically we are iterating neighbors of the source in the graph. If the current ticket is not visited, can we have multiple paths from U to V? Okay, if it's not visited, then we will add it to the visited set and add the next stop dot V we need to add to our itinerary, and then we can call our DFS. So in DFS we need this will be our current this will become our new source, and this itinerary graph and visited set and the size of the number of the tickets. And after visiting a particular path, what we will do, we will backtrack it. We will remove it from, we will remove this particular uh, string from this, and we will also mark it as unvisited. We will also remove it from the visited set. Let's see, let's run the function. Okay, lot of compilation error we are getting. Compute, we need a e here. Okay, so this is fixed. We are returning 0 here, so we need to return true here. Okay, I think now errors are fixed. Okay, we do have one more error. Okay, so we need to put a pair here also. Mm, okay, we are getting wrong output for this particular case. We can see it like we can move the test result here and see the example for which you are failing. So this example solution is this, and what we are returning this solution. So the problem saying another possible reconstruction is this, but it is larger in lexicographical order. Okay, so the output which we are returning is larger in lexicographical order. Means these two can be the possible itineraries, but the one which we are returning is lexicographically larger. We need to return this one. So let's see what uh, issue we are having. So this is our graph for the problem. Let's see if this function is correct or not. So suppose we compare this with this. Okay. So this is our current, let's assume. This will be our itinerary, and this will be okay. So what we are doing, we are iterating. Both have will have same length, so we are starting from zeroth index. So we will check and this and this. Okay. So we have both of these. So one thing we can do is this will not impact the working. We means if current string equals previous, then we can continue. We don't need to process this part. So now we have alt as our current and sfo as our previous. Okay, so we are checking if uh, okay, understood. So we need to decide which is lexicographically smaller. So if our this until it's equal to this, so not a issue. Until then, it's not a issue. When it becomes smaller, means if it becomes smaller, then we can directly say return true. Means if this is smaller than this string, then we can say that this is lexicographically smaller. We don't need to go further. Okay. And what we were doing previously, we were just looking, we were not we were only checking if it's greater. We just calculating if it's not like geographically smaller. We will also need to consider this condition. Let's see if this works. Nice, we are getting TLE. So we are using backtracking, so that is why it is giving TLE. I don't not able to think of a way we can do it better. JFK to SFO. Here we have repeated edges also, like this one. This particular edge is repeated. But we need to visit all the tickets, so it doesn't matter if it has duplicates. JFK ADL, JFK ADL. I think here we need to have some concept. Okay. Hello. Okay, I think we are having some knowledge issue here. We need some concept to solve it. Uh, so this is the force way which we are using. So we need some algorithms to solve it. Let's see my previous submission how I have solved it. The first result, passing this linked list into this graph. We are building graph from these tickets. So we have created this graph from this path to this path. We are adding string to priority queue. Means in priority queue we are basically storing lexicographically uh, smaller string at the top of the priority queue, so that we need not to check this particular thing. We then priority queue will do it for us. Okay, then we have built a graph and we are using a linked list. I don't know why. Then we are getting from this graph, starting from JFK, we are from we are choosing all the destinations we can go from this particular node destinations. I think it's topological sorting, I think. Maybe maybe it was eh, okay. DFS transfer cell starting from JFK. We attempt to visit each destination. And geographically smallest airport next. Okay. You are given a list of states and Okay, we need to find some other way to do this. I'm not able to understand this approach. That's what we are doing here. Okay, equilibrium circuit we need to. So we need to learn this concept equilibrium circuit. Okay, equilibrium path is a path in graph that visits every edge exactly once. Equilibrium circuit is an equilibrium path that starts and ends on the same vertex. Okay. Okay, so first we need to find that our path is equilibrium or not. So let's assume in this particular problem we have equilibrium path. So we are doing. Okay, equilibrium path in directed graph. So what's equilibrium? How can you solve it? For a directed graph to have a equilibrium circuit, a closed path that starts and ends at the same vertex, it must satisfy the following conditions. All the vertices with non-zero degree must be strongly connected. There must be a path between any two vertices. Okay. So in the question we have said that there will be, always be a solution. So the in degree and out degree of every vertex must be equal. Okay. However, for equilibrium path, not necessarily a circuit, the conditions are all the vertices with non-zero degree must be strongly connected. Exactly one vertex must have out degree minus in degree equals to in degree plus 1. This is the starting point. Okay, we do have a starting point already. Degree and out degree after applying path to the problem. This implies that degree now degree. Okay. This set okay. Build the graph. Create a directed graph. Okay.